Good morning. Now, the next topic is about the design of digital filters from analog filters and also analog low pass filter design. So, in your syllabus, the main heading is given as design of digital filters from analog filters, and in that, the first heading is analog low pass filter design. So, today we will learn about all this. Now, this is about a brief theory part about design of digital filters from analog filters. Digital filters are actually made from analog filters and analog techniques, and which have been in study for many years, even before the beginning of digital systems, and it can be used quickly and efficiently to design digital filters. That is the basic design of digital filters comes from analog filters. Analog filters was first designed, and by using certain modifications in the analog filter design, there comes the digital filters. Now, digital filters can be designed using analog design methods by following these steps. First one, the filter specifications are specified in digital domain. The filter type, that is whether it is high pass, low pass, band pass, etc. is specified. Then an equivalent low pass filter design is designed that meets these specifications, and then the analog low pass filter is transformed using spectral transformations into the correct type of filter, and finally the analog filter is transformed into a digital filter using a particular map. So this is how a digital filter is designed by using the basic concepts of analog filter. Now, there are different types of spectral transformations and mapping to convert an analog filter to digital filter. Some of them are bilinear transformation, impulse invariant method, approximation of derivatives, and finally frequency transformation. Now, I am not explaining all these four in detail at present. Why? Because in your syllabus you will have to study each of these in detail. So, we will come to that. So, now for the time being, I just briefly describe each of these four topics. Okay. Bilinear transformation means it is a method which is entirely a frequency domain method, and so some of the optimal properties of analog filter are preserved, that means are conserved. As was the case with impulse invariant method, the time interval is not normalized to 1 but is explicitly denoted by sampling interval t with units of seconds. That is, in bilinear transformation we are concerned about a sampling interval t, which is expressed in units of seconds. Now, the bilinear transformation is nothing but a change of variables, that is mapping, that is linear in both numerator and denominator. Now, impulse invariant method, it convert analog transfer function in frequency domain constraint into digital transfer function using time domain constraint. So, what this method does is that the transfer function of an analog filter which is mentioned in frequency domain is converted to the transfer function of digital filter which is mentioned in time domain. Okay. Now, the digital filter designed by impulse invariant method is required to have an impulse response. That is, any digital filter that is designed using this particular method will have an impulse response which is exactly the same as that of the impulse response of the analog filter. So, any digital filter designed using this method will have an impulse response exactly the same as that of an analog filter. That is, if the analog filter has a transfer function f of s with an impulse response f of t, the impulse response of the digital filter h of n is required to match the samples of f of t. Approximation of derivatives. Here, a differential equation can represent an analog filter. We know that we can use transformations like Z transform to convert a differential equation into a difference equation. Once we have the transfer function of an analog filter, we can use the Z transform to get the transfer function of the corresponding digital filter. So that is, if we actually, the conversion of analog filter to digital filter is nothing but the conversion between the transfer function. So once you get the transfer function of the analog filter, then you can get the corresponding transfer function of the corresponding digital filter by applying Z transform. That is what they are telling. So the approximation by derivative methods is also known by the name backward difference method. Finally, frequency transformation. It uses a frequency mapping to convert the analog filter to a digital filter. It has the desirable property of preserving the optimality of the approximation. Now let us see the derivation of transfer functions for analog and digital filter. Consider analog filter. Its transfer function will be a differential equation of the form y of t is equal to d by dt of x of t. Now, as studied in first semester, we are taking the Laplace transform. So, Laplace transform of y of t is y of s, that is equal to s x of s. Okay. Now, the transfer function of the analog filter can be written as, from this particular equation, y of s divided by x of s. That is, can be written as h of s, that is actually equal to s. Now note that this is just a generic transfer function. Now in order to get the transfer function of a digital filter, we divide into some specifics, that is analog input to analog filter. Here this from this figure we can say that we'll go to the next session, and from that we will understand the meaning of this figure. Next we are going to input a sample analog signal, that is an analog signal is given as input to what, to the analog filter, and we are going to find the transfer function in terms of this analog signal. So we will Z transform this transfer function to get the digital filter transfer function. Okay, as already said, in order to get the transfer function of the corresponding digital filter, what we do, we apply Z transform to the transfer function of the analog filter. So from this figure, y of nt, that is t is a sampling interval, n is the number of times of sampling. See, we subtract between these two. This is x of nt and this is x of nt minus t. So this point is this and this point is, so now we subtract these two quantities divided by their separation t, that is written here. Thus what is y of n, x of n minus x of n minus 1 by t, that is we are taking t is common, that is taken outside. Okay, so we will get this expression. Now taking z transform of y of n is y of z, then x of n will be x of z minus z raised to minus 1 x of z by t. Now on solving y of z by x of z from this equation, what will be, it is represented as h of z and is given by 1 minus z raised to minus 1 by t. That is, we are dividing the LHS and RHS with x of z. Okay, that's how we get this. Now that we have the transfer function for digital filter, we can do the following. What are the steps? Equate this with the transfer function of the analog filter transfer function, and finally replace the value in the place of s in any analog filter transfer function to get digital version of that particular analog filter. This is how we use the transfer function of in order to convert an analog filter from digital filter. Now the second topic, that is analog low pass filter design. So before that we have to understand what an analog filter is. Analog filter is typically used in electronics and is considered as a basic building block of signal processing. They are used to separate audio signals before applying to loudspeakers. To separate and to combine several telephone conversations onto a single channel also we can use analog filters, and also to select a particular radio station from the radio receiver by rejecting all other channels. In that case also we can use analog filters. So that is the definition for analog filters and its uses. Now analog filter design. Analog filter design includes analog filter transfer functions, poles and zeros of analog filters, frequency response of analog filters, output response, and different types of analog filters. So various methods are there in order to design an analog filter. Some of them are Butterworth, Chebyshev, and elliptic methods. Now among that, the most important and the common one is the Butterworth filter. Here the signal processing filter, what is the definition for Butterworth filter? It is defined as a signal processing filter having a flat frequency response. This is a highlight. It has got a flat frequency response in the pass band and can be termed as a Butterworth filter, and is also called as a maximally flat magnitude filter. It is mainly used for shaping the signal's frequency spectrum in communication systems or control systems, and the cutoff frequency is given by this expression. Now let us see about the design of low pass Butterworth filter. The frequency response of Butterworth filter approximation function is often referred to as maximally flat. This term is very important in case of Butterworth filter. That is, there is no ripples, it is flat. So the response is flat because passband is designed to have a frequency response which is as flat as mathematically possible from 0 Hz until the cutoff frequency at -3 decibels with no ripples. That is why its frequency response is said to be flat. Why? Because from this range, that is from 0 Hz to -3 decibel, that is the cutoff frequency, and up to this range, that is from 0 Hz to -3 decibels, the frequency response is completely flat, that is there is no ripples. Now higher the frequencies beyond the cutoff point roll off down to 0 in the stop band at 20 decibels. So the roll of stop band is at this particular frequency 20 decibel per decade. That is a roll of time. This is because it has a quality factor Q of 0.707. So here these are some of the characteristics. That is, it is maximally flat. That is, it doesn't have any frequency, any ripples in this range. That is from 0 Hz to -3 decibels. And what is its roll off rate? 20 decibel per decade. And what is its Q factor? So these are some of the highlights that becomes important while designing a low pass Butterworth filter. Another point that we are concerned while designing a low pass Butterworth filter is the frequency response. As already said, higher the order of the Butterworth filter, then higher will be the cascading possible. Cascading means combining one stage to another, and so higher the order, higher will be the possibility of cascading, and higher will be the brick wall shape, that is this block like shape. Okay. But this ideal frequency response is actually not attainable in practice. Why? Because theoretically, though we say that it is maximally flat, but in practically there will be some ripples, especially in pass band. Now this is a frequency response of a Butterworth filter. This is this equation, and n here, n actually represents the order of the filter. Omega 2 pi f, epsilon is maximum pass band gain. A max is maximum pass band gain. It is defined as frequency equal to cutoff, that is -3 decibel at f of c, that is cutoff frequency, and epsilon will be equal to 1, so epsilon square will be 1 itself, and the value of epsilon can be found by using this equation, that is h1 equal to h0 by root of 1 minus epsilon square. What is h0? Maximum pass band gain. What is h1? Minimum pass band gain. So h0 by h1 will be, from this equation, mathematically it will be this, so its value is this. So epsilon will be 0.508. Now the voltage transfer function h of j omega, it is given by this equation. V out output signal voltage, V in input signal voltage, J square root of -1 omega radian frequency. Then finally transfer function for second order low pass filter. There's no need of learning. So which are the specifications? When they ask you to write this one, then the roll off rate, Q factor, then the expression this about the frequency curve, then about the frequency response equation, explanation of terms, then value of epsilon, this equation, explanation of terms, then finally the transfer function and voltage transfer function, then the result transfer function for a second order low pass filter. So these expressions actually we have to take into consideration while designing a low pass Butterworth filter. So all these terms actually comes while we are writing about the design of a low pass Butterworth filter. Now this no need of by hearting these values. This is just an example to show how you design a low pass Butterworth filter. See, they are asked to find the order of a low pass Butterworth filter, and whose specifications are given by, that is, maximum passband gain is 0.5 decibel and passband frequency omega p is given as 200 radian per second, and minimum passband gain A minimum is minus 20 decibel and the stop band frequency omega is 800 radian per second. So using these specifications you will have to design a low pass Butterworth filter. So for that we have to understand we have to find out the order of the Butterworth filter. So the first step that you do is we find the value of epsilon as already mentioned in the equation from this. So the first step is finding epsilon. So epsilon we got. Okay, now next what we do is minimum stop band gain and all everything is given, and maximum stop band frequency everything is given. So this stop band frequency and all we will have to substitute in the equation to get the filter's frequency response. So the next step after finding epsilon, we are going to find the frequency response by using this particular equation. Okay, so in that you can see an n here. Okay, so this is from this equation that you find n, everything will be given in the equation. So in that, from that you have to find n, which is actually order of the filter. It is order cannot be a decimal, so it should be a whole number. So in the whole number nearest to this is 3. So you understood that the filter that you are going to design is of order 3. So the steps involved, what is it? First you have to find the value of epsilon using this equation. Then next you have to find the frequency response using this equation, and from that you can find the order of the filter. So that is how you have to write, no need of writing all the steps. Okay, now so you got 2 steps. Now the next step is that anyway you have to use a feedback resistance RF and a resistance R1. So here a low pass filter we got it as a third order filter. Order was 3. Okay, in that case for a third order filter the gain A is 2. So we have to find a value of R1 and RF that gives a gain equal to 2. So you got the values. See, gain will be 2 only if the value of RF and R1 is 1 kilo. Then only we will get to the value 2. So after finding the order, if it is 3 order, then its gain will be 2. For that gain, the resistance RF, feedback resistance RF and R1 will be 1. So we are finding the value of RF and R1. Next we are finding the value of omega 0 from passband frequency omega p using this equation. Okay, so omega 0 value we got, and finally we have to find the value of resistors and capacitors used in the circuit. So these are the steps. First, finding the value of epsilon using the equation, then finding frequency response using this equation. Then from that you have to find the value of n, that is order of the filter. Once you get the order of the filter, suppose that it is 3, then its gain will be 2. In order to get a gain 2, the values of feedback resistance RF and the resistor R1 should be 1. So we are finding the value of RF and R1. Once you get, the next step is you have to find omega 0 from the passband frequency omega p. So our final step is finding the value of resistor and capacitor. Then you are demonstrating it with the help of a circuit diagram. So there is no need of studying the circuit diagram. I have just shown it for your reference. Okay, just follow the steps that you have to study. No need of by hearting the values. Okay. Now this highlights I am not describing. It is just for your information. No need of by hearting. And if you find it useful somewhere, okay, then you can study. Just about the Butterworth filter approximation. Just the formulas only. If you find it useful, you can select the slides and you can include in your essay part or something like that. You can select. Okay, so no need of by hearting all this. If you find any of these slides important, or if you want to include it in your essay, then you can take it from there. Everything is written here, each of the terms is explained. Okay, that's all about low pass Butterworth filter design. All these are analog filter designs. Okay, it comes under the heading analog low pass filter design. In the next session we will learn about the next class, that is about Chebyshev low pass filter design. Okay, so for today this is enough. Please go through these notes. Okay, thank you.